everybody. Good to have you back. We are starting our Module 1 for MOOCOR. In this module, we are going to start talking about some of the things that you all know. We are going to go step by step and create the need definitions. It is very important that you start and follow the same steps that I will try to go through for you to get to the point. We will start first by talking about the concept of the solution. In MOOCOR, our approach is to concentrate on the concepts and talk about the concepts, why things are done in a specific way, and what does it mean when we violate some of the rules and conditions that are supposed to be followed. We are not going to concern ourselves with the detailed mathematical definitions. Rather, we will be looking at applications. We are going to be talking about concepts, and these concepts are the ones that we are interested in following and using. First of all, we want to clear what the learning goals of this module are. The first, second, and third topic, three topics that talk mostly about two-dimensional problems, are designed such that it would introduce to you the main concepts of linear programming. It's not much of a use in real world. However, it's a great tool to teach you the concepts of certain important things in linear programming. Concepts such as solution, feasible region, extreme points, optimal solution. All these concepts come into play when we look at sample examples as we go through these modules. The first module, as I mentioned, consists of three topics, mostly discusses these material and will set up for the following modules. In the first topic, we are introducing the concepts related to the feasible region and anything associated with that. To do that, we start by introducing simple concept that all of us know. What is a solution to an equation? Instead of defining it as a mathematical definition, we're just saying a solution is a value for your unknown that when you plug it back into the equation, the both sides agree, or the test is true. The right-hand side and the left-hand side both will happen to be the same thing. And in fact, the key is that they are matching the sign that is between them. If it is an equality sign, then the left-hand side and the right-hand side will be equal. If the sign in between them is less than sign, then the left-hand side will be less than the right-hand side. So a solution is a value or set of values that satisfy those signs and that test that we are performing. The second concept that we are going to talk about is the concept of lines and solutions associated with the lines. All of us are familiar with the ways that lines are plotted in a two-dimensional space. Usually using a slope and a constant, we plot the lines. Usually in the formula such as y equal mx plus b, where m is the slope of the line and b is the constant. In here we are going to use different notations for x and y in terms of x1 representing x and x2 representing y. And these are x sub 1 and x sub 2. We are also going to write them in an organized format in terms of ax1 plus bx2 equals c. It's the same thing. It's the same type of notation, but because we are going to be looking at this type of equations and later on inequalities, and we will be talking about more than two variables, it's a multivariable problem. We will be looking at ax1 plus bx2 plus cx3 plus dx4 and such and such and such, and that would be the way that we will represent the work. So how do we plot a line? In here we are going to be using two intercept points. The intercepts are x1 intercept and x2 intercept. So we will calculate those values by just plugging the intercept values into our equation, and that would give us the line. We will connect the 2 points and that will be our line. For example, for this example that we have in here, we can simply plug the value of 0 for x1 and find out what x2 is, and plug the value for x2 to be 0 and find what x1 is. Now I have 2 points in here, one representing x1 0 and x2 5, and the other one representing x1 2 and x2 0. When I connect these two together, I have plotted the line. Now, where are the solutions for this line? Remember, it has two variables. So every point on this line is the solution to this line. For example, I have identified 3 or 4 points, and as you see, when you plug these values back into the equation of the line, the test is true. Both sides are equal. Now we want also to see what is the role of these coefficient of x1 and x2 and the right hand side values. Take a look at the video that we have to show when I'm changing the values of coefficients of x1, how the line changes, or when I change the coefficient of x2, how the line changes, or the right hand side value. As I change the right hand side value, how would the line change? This concept is important. Look at the equation of this line. Let's find out what the slope of this line is. Note that the slope of the line is only controlled by the coefficient of x1 and x2. The right hand side value has no place in defining the slope of the line. When the right hand side value changes, the line moves parallel to itself, either up or down. And again, this is an important concept that at some point in time we are going to use this concept to actually find solutions of the linear programs. Take a look at this problem that I have in here. In this problem, I do not have an equation. Rather, I have an inequality. Now, in the equation that I had in here, the solution was on the line. What about this case? Where are the solutions to this inequality? Well, in this case, any point, for example, in this case that the sign is less than or equal, any point in here, in this area, is the solution to the problem. How did I find that? By just testing one point. What is the easiest point to test? The origin, 0, 0. So I tested 0, 0. I plugged 0, 0 back into the inequality and saw how it worked. So how do I know about the rest of the points? The solution is on one side of the line. It's either this way or the other way. So if 0, 0 fits into the test and the result is true, then that's where the solution is. To identify that, we usually use arrows at both ends of the line that we have drawn to represent where the solution is. So that's what those little arrows that you see on two ends of the line represent. So what if instead of just less than sign, I had less than or equal sign? What would happen then? Well, the solution is pretty much the same thing. It is the same place, except that because of that equal sign in there, now the line itself is included. What if it was less than sign only? Then the solution is the same, except that the values on the line are not part of the solution set. So let's look at some of the lines that we have drawn in here and see how they work. It's a very simple process to find the solution. First of all, you plot the line. Second of all, you find a test point and use that test point to figure out where the solution is. What if your test point didn't work? Like, for example, this example that we have in here. In here, I changed the sign to greater than or equal. And when I plug 0, 0, I notice that 0 is not greater than or equal the right-hand side. What it is telling me is that 0, 0 is not part of the solution. So if it is not part of the solution, then the other side is the solution. Very simple concept. What if I had more than one equation or inequality? Well, this is an example. Now I've used the same line that I drew before, and I'm adding a different line also in here. Same concept, same approach. I plot that first line, I plot the second line, I find where the solution for each one is by using a test point, and I notice that my solution set is restricted by these two lines. What if I had more than two? Well, here's an example. In here I have 4 inequalities. And as I am plotting each one of them one by one, you will notice that some parts of the solution for each one of them would restrict the final solution set for me. And in this case, this is going to be the solution set. This solution set is called feasible region. So feasible region is actually the solution set for this set of inequalities. There are certain lines that are a little bit different than the others, that we use a different method for them. We use 0, 0 as our test point. Any line that passes through the origin, such as this line, will not allow us to use 0, 0 as the test point, because 0, 0 is on the line. And I will not be able to identify the solution of this inequality. Well, I can either use a different test point. Instead of 0, 0, I can use 0, 1 or 7 and 11, something that would allow me to identify where the solution of this inequality is, or something even little trickier. Remember I told you that if you change the right hand side, the line is only parallel to itself. Well, instead of trying to plot this line, I'm going to plot this line with a different right hand side. Just a value, any value that you are comfortable with. For example, this is the value I selected, and I plot this line. Now if I change the right hand side to 0, what happens? The line which is plotted will move parallel to itself and will pass through the origin. But it is easy to test for the new line and then apply the same to the line that passes through the origin. The new line, for the new line, I can test 0, 0, which will give me the solution as you see on the two ends of the line. It is the same solution when I move the line parallel to itself to pass through the origin. Or when lines only have one of the variables. For example, in this case, only x1 exists. There is no x2, which basically means the coefficient of x2 is 0. So when you want to find the slope is going to be infinity, which basically suggests that this is a vertical line. Or in this case, only x2 exists. The coefficient of x1 is 0. So the slope really is 0, which means it is a horizontal line. So when there is only x2, you're dealing with a horizontal line. When there's only x1, you're dealing with a vertical line. For example, x1 equal 1 is a vertical line that passes through x1 equal 1. Or x2 equal -5 is a horizontal line that passes through x2 equal -5. What about x1 equals 0? It's a vertical line that passes through x1 equals 0, which is basically the x2 axis. What about x2? It's a horizontal line that passes through x2 equals 0, which is basically the horizontal axis, x1 axis. What about x1 greater than 0? What about x2 greater than 0? Now, let's combine all these things into a problem and find out what the feasible region is. And this is the example. You will see that it has a number of less than or equal sign and greater than or equal sign, and including two specific constraints, which says x1 greater than or equal 0 and x2 greater than or equal 0. In reality, x1 greater than or equal 0 and x2 greater than or equal 0 refers to the first quadrant of the Cartesian coordinates that you have drawn. Let's draw that and see how it looks. This feasible region is closed, while the other feasible region was open. It was open here, but this one is closed. So you can have closed feasible region, you can have open feasible regions. A closed feasible region and unbounded feasible region. How many solutions this feasible region have? Infinite number of solutions. Everything inside this area, everything inside this closed area, including the lines, are solutions. What about this one? Same thing. Infinite number of solutions. Everything inside this area is a solution, including the lines. Therefore, we are now talking about infinite number of solutions. Before I go one step further, I want to talk about one little thing. Some of these points that are at the intersection of these lines, the corner points of the feasible region, are very important. We'll talk about them later, but they are very important. These corner points, we call them also extreme points. These extreme points are significant part of optimization process. So for example, in this case, we have 1, 2, 3, 4, as you see, you can count them and see how many extreme points we have. In here, we will have some extreme points. How do we define extreme points? We are saying every two of these inequalities, that every two of these lines that intersect would create an extreme point. Some of the extreme points are feasible. For example, these are feasible. Some of the extreme points are infeasible. So that point, this point, that point, they are all infeasible extreme points. They are extreme points based on the definition, but they are infeasible extreme points. The feasible extreme points are very important, but infeasible extreme points have very much the same type of mathematical significance in operations research. What about this case? Well, it's the same way. You look in here and you can count the number of extreme points and so on. So whether it is an unbounded feasible region or a bounded feasible region, we can identify the extreme points for the set of inequalities that we have for the problem. Before I introduce the next concept, let's consider this. In here I have infinite number of solutions. Which solution is better? Better in terms of what? And the answer to that question is usually a criterion measure, a measure of performance. It said, in relation to this specific function. And if you introduce a function, for example, in here, you will see a function is introduced, and you say, with respect to that function, and then you say, well, what is your goal in respect to that function? And you say, oh, I want to see which one of these solutions will give me the largest number for that function. So our concern is to find the maximum of this function subject to these set of restrictions that will define our feasible region. Whether it's maximization or minimization, that specific function is called performance measure, criterion measure, a measure of performance, objective function. So now we have an objective function we have a set of constraints or restrictions, and now we have something called a linear program. So now we have defined a linear program. A linear programming model consists of an objective function subject to a set of constraints. So that is the model. Just one last thing. How do we find the values of corner points? Well, it's simple. There are two lines, they are intersecting. So you will solve a system of two equations, two variables. And in here, calculation for that extreme point is presented here. Some extreme points are easy to calculate. Some of them are intercept x1 or x2. Some of them are on vertical lines or horizontal lines. This is as much as we are going to cover in topic 1.